Hello and welcome back to my videos series about machine learning. And so I decided that we are going to dive into an example of a strided convolution here because it's something I did not do, and so I was planning to show you how the backpropagation works, and my goal is to go through the backpropagation of a strided convolution because that was what was very hard for me to find a good tutorial for on the internet. I had to kind of mesh together like 2 or 3 sources. But before we go into that, so what is the backpropagation? Why do we have to consider this whole thing? So in the backpropagation, so what we're doing, we are trying to find the derivatives of a function based on either our convolution kernel or our input matrix. So I guess if you are into machine learning already, you probably know that. So in a machine learning, and this is especially we're talking about the neural networks and the convolutional neural networks here. So neural networks are function approximators. It's kind of a combination of different layers. So we could write that like there is okay, let me start a new line somehow here. So final y is going to be some kind of function of another function of another function, f, g, h, a, j, k, l, and there is our input. I guess that's how someone could describe what the convolution is doing. So we got some x, or not convolution, it's just a neural network. It goes through maybe a convolution, maybe another convolution, a fully connected layer, or some activation function, some pooling, whatever. Thing is, in general, we're just thinking about it like a lot of functions fit into each other and how we are trying to optimize these functions. So all these functions have some kind of parameters, or maybe not all. If it's an activation function, it doesn't. Anyway, so these functions usually have some parameters, like maybe this is the convolution we're talking about. So this L has a, like some weights. So it depends on the weights, and I want to find out how to change these weights so that my y, so the output of this whole function, will be as close as possible to the real y value. So I have the real I value and this calculate, and usually like we can do something like take the square, and let's say this is our cost function. So because this is like a, not all of the times this is what, this is an example. So you say that the square of the difference between what you calculated and what the real y value is, that's gonna be some kind of c, a cost. So what you want to do is you want to minimize this cost, and to minimize this cost you should figure out how this cost function changes depending on these weights. So we got the weights for this L function, and we want to figure out, because if we know this how the weights change, so how the cost function changes and the weights change, we can figure out, okay, so if I change the weights in a positive direction, the weights go up, then cost goes down, then I will have to move these weights up a little. And this is how we optimize the function. This is what machine learning is about. This is what learning is. We are trying to figure out the parameters of all these functions so that the real values will be as close to our calculated values as we can do it. And of course, because we'll have a lot of examples, so probably it will never be exactly 0, but we want to minimize it. We want to make it as small as possible. So how do we calculate this? So here, oh, come on. So here we have this neat trick, which is, so let's just simplify this one. I don't want to go all the way in there. So how can I, oh, maybe I cannot delete. Okay, anyways, so let's just delete this whole thing. So it's going to be a function of our other function, which is going to be, let's say, GW, and it's going to be GWX. So we want to figure out how this W, what this W has on the, what W effect has an effect on, how W has an effect on the cost function. So that's what we are going to do. So this is how we are going to basically say that this is the cost function is like depending on the F, and that depends on the G, X, and I have to do it, yeah, and D, W. So this cost function that depends on the F function, so this, anyway, I just say it's C, just like a function, like let's say it's C, y, C, y, C, y equals like this. Okay, so we have the chain rule for this, which means that if I calculate, I can calculate this by calculating dc over, so it's a dcf, df, derivative by the f function, times, or let's use this sign, times df g the g, and then we use d g, and we have gw here actually, or dw. So this is what the backpropagation is basically. So when we are getting to this convolution, we already have this part calculated, and basically what we want to do is just calculate the derivative, this one, this derivative. So that's why we need to know, so because the convolution is nothing else but a linear combination, so it's these W values, which are represented here, are just simply multiplied by some parts of these numbers and then added together. So it's linear combination, literally. And in a linear combination, we have this very nice thing that D, like let's say AX plus BX, if we just want, anyway, let's just say it like this, over dx, it is equal A. So basically, this is like, let's say this is weight, so let's just be consistent here with notations. So we have this bias vector, maybe a bias, we have this weight over x. So this is now another vector. This is like, let's just say this is scalar. So this is just one number x, or rather here we want to get the w, and that's gonna be x. So there, of course, we will have more complicated, like weight 1 will be multiplied by, you know, x2, and then in other parts we will have the same weight 1 multiplied by x3, so then it will be, come on, oh, what am I doing? So it will be x2 plus x3. So that's why. So this is my whole rambling about all this backpropagation. So this is why we have to know exactly which weights are multiplied by which parts of this x, and this is what our backpropagation in the convolution will be dependent on. And this is kind of, if you don't have any striding, just stride 1, then it's kind of very easy. You can find it very easily on the internet. It's just basically another, you have to do a convolution operation on the backwards, basically. So anyways, so this will be, you know, like a lot of y. Actually, what we will get is like the derivative by y, which is, you know, here is GW is what our convolution here will have as a y matrix. This y matrix or y tensor will be this GW, and then this will, what we will get is like derivative by that y. So that's why. Yeah, so let's calculate. Let's do our first convolution calculation here. So bear with me, I'm gonna do it by hand as usual. So we multiply. This is linear combination. So last time, oops, we talked about how you can speed up this operation, make it faster by making a vectorized version of your input. So we got, oh, and this already screwed up because I wanted to show you also the padding. So we pad by 0. We pad it with zeros, and I already screwed it up. Okay, I guess it's time to move these little cells one by one. So this is gonna be the left right corner of our output, and as I should be doing the, wow, what button have I pressed right here? So I should be putting the dollar signs here. So the convolution operation will be fixed. The kernel, the convolution kernel will be fixed and won't move away. Okay, so let's move 1. So now I moved 1, but we have a stride of 2, so I want to move these little cells a little more. And let's press another enter, and then now I guess if I do like this, oh no, why not? Do I have to do it all by myself, by my hands? Okay, then I will give up after this, so I'm not gonna, damn, yeah, that's why I'm gonna give up, because I'm not gonna do this whole thing with the everything here, so I needed one more and one more, so I needed 5 by 5 to finish this. I will just do this this part, and I will use this part of this convolution to show you what I want as soon as I can do this striding. Maybe it would have been a better idea to prepare this beforehand, but I really wanted to, you to be with me here as I am setting up these tiles, these little squares here, so you can kind of see visually how these things come together. And I should probably have zoomed in on this. If you are watching this video on a mobile device and not on a full screen 4K TV, maybe you don't really see what I'm doing here, so let me zoom in as much as I can. So, as I said, the whole thing should be this big. So I have not finished the whole matrix there. Maybe I'll just move one step back. So what we have here, so this 9 cells from which these parts, so these are zeros, these are padded, and these are zeros, these are padded. So like this one goes from there, this one goes from there, this one goes from there. So we have 1, 2, and 3 parts. Right? No, what did I do wrong here? Yeah, I did everything wrong here. So these parts actually, I screwed these parts up. Come on. How am I even doing this? Okay, so now that I zoomed in, I was saying it's much easier for me to do this, but that was not true. So let's just try to be precise with our mouse movements. Okay, so we got this part here, this part here, this part here, this part here, and this part here. Okay, now, so as you can see, this convolution is taking steps here. So when I want to do the backpropagation, what I will get is I will get a matrix that will say that each one of these, if I change this 4 to 5, that's just very broadly speaking. So derivative is saying that if I change this a little to a little higher number, then I would get, I don't know, a little higher cost function, or even just change it a little, but my cost function would go very down. So then I just need to change it a little that way. So, but how do I change that? So I need to figure out how these components, take part in this. And what's important is that when you calculate, when you do the backprop, you need to know each of these fields, each of these elements in the kernel, what elements of the input tensor are they going to be paired up with. So here, because I did not do the whole thing, let's just say this one. So this one, I want to know what is this one paired up with. So I can see here it's paired up with, so this is what it is. This is N3, it's paired up with D4, of course. Here it's paired up with F4. Here it's paired up with H4, so this element. Here it's paired up with this element, D6. and then it's so I have to kind of get all these elements which are kind of separated from each other to form, as here you can see, like which ones are the x's that are influencing that, and then get those x's and basically you have to like add them together somehow. And of course you should also not forget that you have to multiply by, you know, what the things that came before. So that's how that works. So what I want to do here is why I can probably so yeah, this is how it works. So these are which parts these things come from. But unfortunately, it cannot really show what I really want to show. Like if I want this element of the kernel, which will be this multiplied by this one, it will be this one, it will be this one, it will be this one. Am I right? Yeah, with this here, like this is central element, so this will kind of get these parts. So when I want to get the backpropagation, what I will have to do is I will kind of have to multiply these values by, you know, what came before, the derivatives by our next layer, and I have to multiply them in a meaningful way. So, you know, this 4 came from this 6, this 3 came from this 3, this -1 came from this 5, this 2 came from here, and yeah, we will probably, yeah, this will not gonna be 5 by 5, this is gonna be 4 by 4. Oh my. Anyways, let's trust the computer with this. Let's trust our Python program with this. So I have this 2 matrices here prepared, and I will do just tried convolution. Here, of course, our convolution layer needs these in a different way. It's a 4-dimensional tensor, so it's gonna be x. It's gonna be a dot reshape, and it's gonna be 1 1 8 8, and the weight will be b dot reshape. It's gonna be 1 1 3 3, and let's make our convolution layer as conv layer and output layer 1, input layer 1, kernel size 3, padding 1, stride 2. That's how we're gonna roll with this. And let's set the kernel w, and we will have a 0 for the bias, and then let's set the input as x, and let's convolve, and it's a 4x4 matrix. That's what we can compare. It's 4 3 -1 and 2, and it's 2 1 -1. Yeah, 4 3 -1 2 1 -1. We were very good at that. So basically that's what happened, is like because of the striding, this convolution it got, you know, smaller. So basically if I got like a L2, let's make it a convolution layer of the same size, but just let's take one padding and one stride. So keep the padding but add the stride, and I'll set the kernel oh, it's L2. What am I doing here? To set kernel, it's gonna be W and NP dot array and only 1 0 in that array, and then yeah, it's not MP, it's NP, it's numpy, and then L2 dot set input X, and let's L2 dot convol, and let's also do just L dot convol here, and let's just see like this 4 is here, this 3 is here, this -1 is here, this 2 is here, this 2 is here, this 7 is this 7, this 23 is this 23. So basically what we got in when we are doing the strided convolution is we are leaving out parts of this the final Y matrix we are producing, and when we are receiving, so we will receive the dy, so the derivative of the cost function by the output of, so by the next layer, which is the output of this layer anyways, then we will have to be cautious about that, and then what I will show you how I did in the next video, and until then, bye bye.